Title of our talk this afternoon is New High-Frequency Transformer Topologies. I co-authored this with Bill Tebow, who presently works at Hamilton Standard Corporation. This work was undertaken as a result of some early work from a customer that dealt with electronic coils in Springfield, Massachusetts, who wanted a 175 megahertz transformer with about 75 ohms impedance on it. Wanted it small, wanted it flat, and wanted it lightweight, all of which don't necessarily go with high frequencies. So we decided to take a relatively simple approach to it and look at what the problems were, trying to solve these problems one by looking at the materials. Well, we looked at the useful frequency range. The useful frequency range that we had to define would really tell us the type of material that we have. We knew that 175 megahertz was at least at the top, but we had to give ourselves a margin of error around the sides. The amplitude of the excitation wave. You want to know where you are on that BH curve. What type of excitation you have. Where you are going to be with respect to B and H. A method of measuring inductance on the transformer. Method of measuring impedance, something that everyone would agree with. And finally, the frequency response and the effective permeability of the resulting materials. Would these be in line with, or at least better than, the existing materials and lending themselves to a flat topology, which is what we were looking at? So we set ourselves some target values for the nickel zinc ferrite. Nickel zinc because the manganese zinc ferrite cuts off at the level of about 3 megahertz or so. We went to nickel zinc because nickel zinc chemistries are very easy to deal with. We wanted an initial permeability of somewhere between 10 and 100, a Curie temperature of over 250 degrees centigrade, a flux density from 1,000 to 3,000 Gauss, and a magnetic field intensity that was in the range of 100 to 200. Loss factor, which is tan delta over mu sub I, somewhere's in the range of 300 to 1,000 times 10 to the minus 6. And typical frequency range of 5 to 100 megahertz. Well, if it were going to be 100 megahertz, that would be all right. But we needed 175. So we had to sort of push the state of the art on the present nickel zinc because the fall off on present nickel zinc usually starts somewhere around 100 megahertz. What could we do to change this formulation, to change this pattern of behavior of the high frequency materials and still keep the properties that we wanted for the high frequency transformer? Well, we went to a flat or pancake topology, well defined in its equations by the radius, the effective radius of the material, the width of the coil, the width of the wire itself, and the central diameter of the coil, where the prime amount of the ferrite material would be. Very well defined in Weber's book as far back as 1965. Looking at the layered design, it consisted of a bottom layer, usually the primary, and a top layer, which was secondary, with the ferrite surrounding it. In other words, the windings embedded in the ferrite. And you say to yourself immediately, there goes the capacitance. Not necessarily. If we can control the resistivity to be above 10 to the 9th ohm centimeters, and keep the dielectric constant, or at least the effective dielectric constant, quite low, then we might be able to handle what we need to handle with respect to all the parameters in this transformer. The equivalent circuit of this material winding synergy is much like any other high frequency involving its interwinding capacitance, its primary to secondary capacitance, its leakage inductance, its leakage resistance, which is effectively your loss tangent associated with it. So we're not dealing with anything new with regard to the equivalent circuit. What we really had to look at was what could we do to make these very predictable, minimize our losses, and maximize our permeability. How would we measure it? We measured it with an 8000 series network analyzer from Hewlett-Packard, with a splitter going into a reference and the unknown. On the basis of this, we hoped that we would be able to get some type of standardization, as shown in the next picture. We actually did measure our 75 ohm impedance at 175 megahertz. And this went after 3 designs. 3 designs involved in changing expansion coefficients, changing the number of windings, and zeroing in on the type of material that we wanted. As you can see from the network analyzer picture, we have peaks sitting exactly where we want them to sit, and a frequency response looking like we're at least getting 30 dB up from our gain from our transformer, meaning that there are really minimal losses. Windings in the coil, showing us that we could do this with bare windings and then embed the ferrite around it. We did this on a regular coil winder and restricted the length of the coil wind, made it a single winding, multiple layer coil, as you can see. We decided to go to a sol gel technology for our material technology, knowing that we'd have control of our particle size, our morphology, our chemistry, and still keep the stoichiometry of the material itself intact. As you can see from the slide, the material starts out as a sol, with the material suspended in this sol, or solution type of matrix, leading down to a gelled matrix where it is flexibly semi-rigid, and then dropping out as a precipitate where we get an agglomeration of particles together, making up the material that we want to use. These particles now range anywhere from 10 to 100 nanometers, and a cluster usually in packets of about anywhere from 10 to 30 individual particles. So we do have control of the particles. However, there is another control mechanism which is involved here, and that is pH. If we look at an acidic generated, or something down in the 6.2 to 6.4 region, we end up with a stringy, interconnected grouping of magnetic material. Once again, nanometer size, but very stringy in nature. Long aspect ratios. If we go up to the basic side, up at about 11, 10.3 to 11, we notice that they are particulate clusters connected by very shallow strings. So we do get different material based upon the pH changes. Extremely different. And this is our control mechanism, because the behavior magnetically is appreciably different in a basically derived material and an acidically derived material. The photomicrographs that we have from the scanning electron microscope show in this picture some of the basically derived materials at about a reading of about pH 10.3. As you can see, the clusters with the short connections to the other clusters. As we said, this material holds its integrity from particle generation to embedment. This is a section in polyester where we loaded to about 30 or 40% so we could see through. It holds its integrity in its clustering. It's a very different type of material. This is an acidically derived material, and you can see the long strands of the ferrimagnetic material. Very interesting material in that it has very directional properties. This is a standard screen printer with all of the normal types of controls on it. The material is relatively Newtonian, and only towards the end of a high pressure cycle does it become non-Newtonian. So we have good control in the screen printing. It screen prints like anything else. We can adjust the viscosities. For the material to be burned off as a ceramic, we use a butyl cellulose as one of the materials, or butylated methyl cellulose as another type of the material. For the plastics, we stuck with polyesters because they were easy to deal with. The materials in the ceramic form were fired at temperatures around 600, maximum about 630. For the plastic materials, they were just baked at a temperature of 120 to cure the polyester. No big deal, up to 60% loading, and we ended up with a pretty consistent material. The conductor dielectric firing was done in standard types of furnaces, and the baking was done in standard ovens. Nothing particular, out in the open, no controls on them, other than just the temperature. As you can see here, the BH curve, the flux density versus the magnetic field intensity for this material, gives you an early region which appears to be very low initial permeability. In fact, it's over 20. And the later region, or the higher excitation region, sitting in the range of over 400. Now, at 175 megahertz, this is pretty good. This is really a pretty good material. So looking at this, we say, yes, it can be done. Are there differences? Of course there are differences. This happens to be a polymeric one. One that's fired as a ceramic isn't that much different, but there are differences in their behavior, especially in the shapes of the curves. As you see here, we have one that is a discrete chip that we wanted to make for surface mounting that was put on an aluminum substrate, a chip that is of the order of about 2 millimeters in width and length. Put onto the substrate and fired in the fashion common to hybrid on an aluminum substrate. This is a 600 megahertz SAW VCO for a fiber optic data transmitter. And we have tried this as of late in order to see what happens up at 650 megahertz. Now this performs with fairly good, yet unmeasured and reported on, but maybe next year we'll have something on that. We were very surprised and very pleased with the results of these tests. So some of our results that we've seen from this. Number one, we know a lot of things that don't work. But we do know that the flat topologies are very viable with thick film types of modalities. Sol gel materials give better frequency response because you can control the size, you can control the pH, and you can get better property control with sol gel. Early tests on nickel zinc ferrites are very promising. And we are going to be doing quite a bit of work further on the formulations, the topologies, firing cycles, and how we actually separate the particles. What is the minimum domain size? How do these behave under different frequencies? What does it look like on a swept permeability versus frequency curve? I'd like to at this time thank Chuck Spaulding, the former president of Electronic Coils, for initiating this project and giving me a lot of inspiration along the way. I've known Chuck for a number of years, and it's much appreciated. In addition, we'd like to thank Mr. Harold Swanson of Allied Signal and Mr. Robert Sanchez of Sandia Laboratories for their critical evaluation in the concept stage on this, and giving me some honest opinions as to where they thought I was right, where they thought we were wrong. And once again, thanking Bill Tebow for putting up with me during this project. Thanks very much.